Exomoons aren't planets, but they might be where life begins. How can life exist on moons? And how different would those aliens be from us? With decades of intense research, millions of dollars, and countless of trial and errors, moons could be where life begins as of lately. When searching for life beyond the solar system, exoplanets usually get all the attention. After all, they're easy to imagine as Earth-like worlds. But just recently, exomoons are gaining traction, as they may hold greater potential for alien life for many reasons. In our solar system alone, there are around 300 moons, and that's just a single star system. 19 of them are massive enough to mold into spheres under their own gravity, known as major moons. Taking this fact to every star system we've discovered so far, the amount of exomoons quickly outnumber exoplanets. Moons have access to energy sources planets may not. While planets rely solely on their star's energy, moons can additionally benefit from tidal heating, when the gravity of the planet stretches and compresses the shape of the moon, creating internal friction and heat. Europa, one of Jupiter's moons, hides a deep subsurface ocean kept warm due to this very mechanism below its 25-kilometer thick icy surface. Not only that, moons can also get protection from cosmic and solar radiation by being within the planet's magnetic field, creating safer conditions for life. Or even better, generating its own magnetic field just like Ganymede. Our solar system offers a glimpse to the unimaginable diversity of possibly trillions of exomoons in our universe. In our system, major moons such as Titan have atmospheres with thick clouds and lakes of methane, Io being volcanically active, and scientists have already sent out Clipper to search for alien life within the oceans of Europa. Who knows what exomoons are hiding from us? As of 2024, not a single exomoon has been confirmed. Compared to exoplanets, they're much fainter and smaller, making it a lot more difficult to detect. Although scientists generally expect that most other star systems should have moons as common as ours, because there isn't a good reason to suggest otherwise. Even if they're hard to detect, what methods do we have in our arsenal? Astronomers propose clever methods to find hints of exomoons by borrowing the same techniques for searching exoplanets as well. When a planet passes by a star, it creates a dip in the star's brightness periodically. This method, called the transit light curve, has been the most successful tool for finding exoplanets so far. In 2016, astronomers used this method on their Kepler Space Telescope to discover exoplanet Kepler 1625b, a gas giant up to 11 times the mass of Jupiter. Its transits were easy to detect. Deep, unmistakable dips in the light from the star. Then, something unexpected happened. Hours after the planet fully passed the star, a second smaller dip was detected. Could this really be a sign of a moon? A year later, astronomers used the Hubble Space Telescope, something much more precise than Kepler, to observe the transit and saw the secondary dip again. Not just this, but the transit occurred an hour and 12 minutes earlier than expected. Every transit of a planet should be periodic if there are no external forces. However, a moon would cause gravitational tugging that could slow down or speed up a planet's orbit, depending on its position, making a year slightly shorter or longer. This causes the timing of its transits to shift slightly, known as transit timing variations. Earth's is around a few minutes at most, since our moon isn't that big. Except a moon with a mass of Neptune around Kepler 1625b would explain the 72-minute variation well. After many attempts to falsify the hypothesis of a moon, proposing other hypotheses such as noise, data artifacts, or even a second smaller planet, nothing fits the observations better than one. The leading explanation? A Neptune-sized moon, now called Kepler 1625b-I, orbiting around Kepler 1625b. As of today, it stands to be the strongest exomoon candidate discovered. The reason why it's still not confirmed is because it needs more data to absolutely make sure other variables aren't on the table. Other exomoon candidates have been identified, such as in the DH Tauri system. DH Tauri b, a planet located in a young system, was observed having a circumplanetary disk made of gas and dust. However, the disk had gaps and asymmetries, which could be from gravitational disturbances from an unknown mass, like a planet or a moon. Yet further studies suggested that the gravitational mass disturbing the disk would need to be as massive as Jupiter, and moons that large are just very unlikely to exist, so it is more likely to be a binary planet system. If life actually exists on exomoons, how do we detect their biosignatures, observable traits, or chemical markers? Scientists made various techniques that can theoretically detect these signs, ranging from atmospheric analysis to studying unusual energy patterns. When an exomoon orbits in front of its host star, starlight passes through its atmosphere and the molecules absorb specific wavelength, creating an absorption fingerprint that reveals their composition. This allows us to see what the air is made of there, a method called transmission spectroscopy. Except on Earth, oxygen is mainly produced by photosynthetic organisms, while methane is released by microbes and decaying organic matter. Without life, they naturally react with sunlight to form carbon dioxide, depleting both gases over time. If we detect an exomoon's atmosphere with a disproportionate amount of methane and oxygen, it signals that there is a process that constantly replenishes the two resources, unlikely to come from physical processes alone, and could point to a presence of organisms replacing these gases continuously. But there is also a similar method called infrared spectroscopy, which detects heat emissions from the moon. In the infrared spectrum, we can analyze the types of gases that may be emitted from the exomoon's surface or atmosphere. For example, the detection of water vapor in the air combined with signs of volcanic activity on the surface shows conditions favorable to life. These are processes we see here on Earth that may support life, such as the deep ocean vents where extremophiles thrive in extreme conditions. Vegetative life on Earth leaves distinct fingerprints. When sunlight hits the leaves of plants, most of the visible light is absorbed for photosynthesis, while infrared heat is reflected to avoid overheating during photosynthesizing. This causes what's known as the vegetation red edge, a sharp spike in reflectance right below the visible spectrum, around 700 to 800 nanometers. It's a unique signature, one that's so strongly associated with life on Earth that scientists have proposed using it to detect alien vegetation on exoplanets and exomoons. However, planets with different types of stars will receive vastly different types of light. A planet around a red dwarf star, for example, would receive more infrared light and much less visible light compared to a planet orbiting a sun-like star. This could push the red edge further into the infrared spectrum, or even into the microwave range. This is because plants would evolve to absorb the light most available to them. For red dwarfs, that would mean infrared light, changing the biosignature we would typically expect to see on Earth. Though these are only clues of life as we know it. On alien worlds, life could emerge from entirely different chemistries. What kind of life are we talking about? Take Titan for example. On moons that have flowing liquid methane through rivers and lakes, life might use methane as a solvent instead of water. These organisms could rely on methane instead of oxygen, called methanogenesis. Such exotic life would operate at a much lower temperature, with biochemistry that is slower and more energy efficient. But Titan is just the beginning. Imagine a moon subjected to intense tidal heating, locked in a perpetual geological disruption from gravitational interactions with its host planet. In such an environment, if a moon were to have an atmosphere, it would slowly be stripped away by the planet's gravity and solar winds. However, volcanoes can release heavy gases like sulfur dioxide, which is more unlikely to escape, in addition to volcanic activity spewing enough material to replace it continuously. Just like Earth's hydrothermal vent communities, These conditions may create ecosystems where energy comes from chemosynthesis rather than photosynthesis. Sulfur-based metabolisms would challenge our ideas of where life can emerge in alien environments, forming ecosystems fundamentally distinct from anything found on Earth. The search for life on exomoons isn't just about refining astrobiological models for the sake of knowledge. It can potentially lead to revolutionary breakthroughs in bioengineering, medicine, and material science. Learning how life survives in extreme conditions may inspire solutions to challenges like cancer, aging, or climate adaptation. And if we find intelligent life, they could be existential threats or offer opportunities for collaboration, rewrite humanity's ways on policies, defense, and ethics. Perhaps the greatest lesson exomoons could teach us is that life doesn't conform to expectations. It finds a way, where and how we least expect it. The question is, will we be ready to recognize it when we find it?